Well, we're back at the science cave, and today we're going to talk about adiabatic heating and cooling. Now, if I can get my pen going here. So, adiabatic. When you talk about adiabatic heating and cooling, you've got a change in temperature. It's a change in temp without a change in heat. This is strictly due to a change in the pressure. As now, let's say we got the surface of the Earth here, and let's say we got a parcel of air here. Let's say we got some air. As it rises, we know pressure, and we've graphed this, pressure decreases. Well, as you go up in the atmosphere, if pressure decreases, that means the particles spread apart. If the particles spread apart, they don't come in contact with each other as much. Therefore, temperature will decrease. Likewise, if air is moving down, and we can think of air as moving down. Whoops, let's see if we can get this going. If air, parcel air, is moving down, we know pressure increases. So the particles get closer together. If they get closer together, they're going to hit each other more, and we know if they hit each other more, they get more friction, so therefore temperature will increase. Temperature increases. A good way to see this, if you've ever had, take a bag of potato chips, put it close to your face and open up the bag of potato chips, and you can feel a little bit of cool air coming out of the bag of potato chips. The bag of potato chips is packaged under pressure. So when you release that pressure, the particles move apart, therefore temperature will go down. If you had a CO2 pistol or anything, when you release the CO2 cartridge, the pressure is decreased, the temperature goes down. Another one like this, your propane tanks for your gas grills. If you ever open it up and felt the top of the propane tank, the pressure decreases, particles move apart, so the temperature goes down. Well, when you think about this, we're going to take a look at some air here. And let's see if we can get a different color here. And we're going to take a look at a parcel of air. And this is maybe the easiest way to think of this. We got some air here. As it rises in the atmosphere, as it goes up in the atmosphere, we know the temperature will decrease because pressure decreases. And for unsaturated air, it decreases at a rate of 10 degrees Celsius per 1,000 meters. And so when air rises in the atmosphere, that's what ends up happening. For every 1,000 meters, it's going to drop at 10 degrees. Now, when you talk, and that is called the dry adiabatic rate. So we're going to put that term in here. That is the dry adiabatic. And again, adiabatic is a change in temperature due to a change in pressure. You're not adding heat, you're not taking heat away. Well, the neat thing about this, and we're going to talk about this in the terms of clouds, and let's get our surface of the Earth here. And again, let's take a parcel of air. We know we take our parcel of air, as it rises, the air cools. And it cools at a rate of 10 degrees per 1,000 meters. But it's going to get to that point where we're going to get some clouds being formed. And where we get the clouds being formed is called the dew point. So as air rises, it cools, and as it cools, those molecules get closer and closer together until finally whatever water vapor is in there is going to start to condense, and that's called the dew point, and that's the bottom of the clouds. This is also 100% relative humidity. It's also the saturation point. When something is saturated, it can't hold anymore. Well, what's kind of neat, and we learned about this whole idea of latent energy. As water condenses, it releases latent energy. So as the water condenses, what happens is energy inside the cloud, energy is released. So inside the cloud, the temperature is actually warmer. Whoops, let's see. Oh, I don't want that one. Let's get rid of this one. So let's take our parcel, let's take our cloud. We've got our cloud here. We have our cloud, so this is the dew point, the bottom of the cloud. Well, what do we have inside here is that all this water molecules, all this water vapor is condensing and it's releasing energy. So what ends up happening, the inside of the cloud has a higher temperature than the outside. So the inside has a higher temperature than the outside. Inside is a greater temp than the outside. The inside of the cloud, as it's rising in the atmosphere, so if we go up another 1,000 meters, we know the outside of the cloud is dropping about 10 degrees Celsius per 1,000 meters. Well, the inside of the cloud is dropping about 5 to 9 degrees Celsius per 1,000 meters. Quite often you'll see the term, they'll take the average and they'll talk about it'll drop at 7 degrees Celsius per 1,000 meters. So what that is saying is that the inside of the cloud is warmer than the surrounding air. Well, if something is warmer, it is going to rise. And that cloud will keep on rising until all the water vapor has condensed. And once the water vapor has condensed, there's no longer any energy. And this is that whole idea when you watch clouds form. It's the water vapor, it's that latent energy given off that really is the mechanism which drives storms, which drives weather. We're going to do a little activity later this week looking at how to actually calculate the point at which condensation takes place and the point at which the clouds will form and the point at which when it comes down the other side of the mountain, what's going to happen is you're going to actually get a warming. And we'll take a look at this in class on Thursday. So make sure Thursday we'll look at some calculations and we'll take some good notes there. So we got to remember one thing is if it cools on one side, when it drops, it's going to warm at the same rate. And that's very, very important. And Thursday is going to be an important day when we look at this whole idea of adiabatic heating and cooling. So that's it for now.